Welcome to the next tutorial. This time about algorithms. As this is a course about applied computer science, we won't do theoretical inspections of algorithms, so that we won't calculate the big O notations. We want to play with algorithms, so therefore you should play a little bit with these things what you heard in the lesson. And therefore we do programming. So we have 3 tasks here. The first task is playing with bubble sort, which you heard in the lesson. The complete or the main part of this program is available in the video and in the download script, and the rest deals with the recursion. So let's start with the first task here. The first task is about bubble sort, and you should take this bubble sort program from the lesson and create a random vector of numbers to use a dynamically changing plot bar, which shows the functionality of each step to sort the list of numbers. So therefore, let's do this in our MATLAB program. In the script, you find this nested for loops. It uses the vector numbers and orders the numbers in this vector in an ascending way. So it's represented here. You have a list of numbers, and after the bubble sort run, after the run of these for loops, you will have this situation here. Again, it compares each number with each other. It's a little bit optimized here because it just runs to the already existing length. But in principle, we have now to copy this into a script. So let's do this. I prepared a script here, which is called bubble sort step by step, and I can call this. So first of all, I copy exactly these lines of code into my script. And then, of course, I have to prepare numbers. So in my case, in the first step, I want to prepare numbers with a descending list of numbers from 1 to 100. So, and if we let this program run, then we will see that it is a sorting mechanism which creates an ascending setup. So that we see what is the change, we can display the input. Sorry, it's called numbers. And we can display the output. And of course, we always start our programs with clear all, close all, and CLC. So let's run this program, and what you get is this. The first output here is the descending list, and the rest here is an ascending list. So the program does what it should do, and therefore we have to continue with the programming now. As a first extension, we want to add the graphical output so that we see some bars which represent the numbers. So in MATLAB, we can use the function bars, and what we do is we first of all display the bars of the original input vector. So bars numbers will plot this. I don't print it anymore because it's not so interesting, and here also because we directly see it in the graphical output. And then I will give an additional short pause so that the program waits on my return input. And we do this after each step here. So each time if we do sorting, we print the bars, and we do a short pause, not waiting for an input of the return key, but we just wait for 0.01 seconds. So with this, we are now able to show the functionality of the program with the output of these graphs here. So, and if I start, I have to enter the return key, and then it will start with a rearranging. Okay, so and now I interrupt this, and now we want to add an additional vector which is randomized, so that we have a randomized set of numbers. In my case, I want to define the size of the original vector. So in our case, for example, 100, so that we use this size here. And then we replace these numbers with a new set, which is based on a randomized creation. And MATLAB offers the ran function, where we can enter the size, for example, e.g., let's say 10, in our case here, 1, so that you get a column vector with randomized numbers. For our plotting and for our processing, it's easier to see integer numbers, so therefore we can multiply them here, in this case, with 10 or with 100, so that you see the randomized numbers in a version where we have a possibility to create integer numbers. And the integer numbers can be created with floor, with round, or you can just convert it to integer 32, for example. You already learned this in your lesson about the binary format, or about the binary numbers, and where you read the binary format from the satellite altimetry. And if you do this, then you will have binary numbers, and they are integer numbers. So if we use this function here to create our vector, and if we use the size vector here instead of the 10, then we can create numbers from this randomized set. If you run the program, you will see how it works. So let's start the program, and you will see the starting situation. And what bubble sort here does is, due to this full which just stops at I, which is here the value here, it will take this number and it will shift it as long as it finds a larger number, and then it will keep this situation and it will take the larger number and it will shift it to the rest. So for example, it will take this and will move it as long as it finds a larger number, and then it will keep this situation and it will take the larger number and shifts to the rest. So it's already an optimized bubble sort. It's not just comparing all of these possibilities, so that it does not do all of the comparisons here. So and I can show you this. So if I start this program, I push the return key, and then you will see this. So, and with the randomized numbers, it's a faster solution than with the limit number, where we have a descending order, so that a complete shift from the left to the right is always necessary. So you see, it's a very nice tool and a very simple program which helps to sort numbers. Let's do a larger size, for example 50 numbers. Let's run again. So play a little bit with this stuff, and we start. you see what happens. And if you have local ordered situations, so that there are local ascending situations, with this optimization you will also keep this, and therefore sorted elements like here will be kept. They are just shifted a little bit to the right, and this is quite a nice tool and quite nice program. But of course merge sort is much faster. Okay, finish. So let's go back to our task sheet. The next task is about the recursion. And you find in the lesson this function ts recursive, which calls itself, it's a nonsense function, so it does not do any practical work, but it shows and it helps us with a very simple setup what you or how you can deal with recursion. So what you see here is the function. It does not return anything. It has just one insert argument. It's the call hierarchy which you define outside, and then it adds a 1 to the call hierarchy, and then it starts a loop here with 3 loops or 3 iterations, and each time it checks if the call hierarchy, this hierarchy, not the loop iterator, the call hierarchy, is larger than 3 or larger than 2. If it is larger than 2, it stops. So if it is smaller than or smaller than or equal than 2, then it calls itself again. So with this you can start to play a little bit with this recursion, because with this small program maybe you directly understand what happens. Before we do this, I want to show you again what this recursion means with a small similarity of using staircases. So let's do this. Recursion is something like walking on staircases. It's a nice image which you can keep in mind if you do this. So each time you step up to the next step is a function call, and the function is the same which you're currently in. So you call yourself, and then at each time you can take something with you. It's the argument which you hand over, and then you jump to the next step and the next step, and each time if you step down, then it's something like losing the information which you leave there. So you have to take things on the way back which you want to use later on here on the lower ground level. So let's do this. I want to show you a sample. So let's start with the sample that we have a number 2, which we take with us to the processing up to the staircases. So what I do is I pack this number into my bag. So this is the argument, and then I woke up. So let's do this. I jump up to the next step. It's the function call. So if I'm here at the next step, I can use this what I have in my bag. So I again use this, and in my case I multiply it with 2. So the result is 4. So at this level the result is 4. What happens is that there at the lower level, before the call happened, everything is already in the memory. So I have a new memory level, a new stack level where this information is now available. And this is because the function, or everything what happens in the function body, is a local memory. So if I jump to the next level, I have a new local memory. And if I jump back, I lose this local memory. So what do? I call the same function again. So I call myself again. I take the 4 now with me up to the next staircase. So let's do this. I take this and put it to the next staircase. So I call the function again and I jump up. So at this level, I take my argument again, put it out. But at this level, from there, I took 4. So therefore, at the next level, at the next local memory, I have the 8 here, because I do 4 times 2. I do the same calculation again, and I step up. So I do the same thing again. Let's take the bag, and let's jump up. Same again, and again. So I can always use what I have in my bag. So remember that all of the steps down here are in the memory now. So if I return from the function call, I forget this here, and I will come back to the level which I reached, so to the memory state which I reached. So all of the staircases which I climbed up are something like elements on the stack. So I put a new element on the stack, which is my function body, with everything, all of the memory elements which I created at this level. So if I return, if I step back, if I do this, I arrive here, and what I have is I forget everything what is here. So I really forget this stack element. So I'm back in my memory element which existed before. So if I do this again, and if I climb down, I'm back at the ground element, and at this ground element I have the existing 2 again. So this 2 which I used for the start. So everything what I calculated was done, but is forgotten now. So therefore, if I print, what I have available is the 2. So everything what I did before is forgotten. So only the existing memory which with I started exists. So that's the case for the memory in function. So if I want to take memory back, I have to do the same. So I climb up again, and here at this point I have to remember. So what do I have to do? I have to bring my result back to the lower level. So I have to pack it and I have to bring it back. This is the return. So I return now a value. So for example, here I return the 32 at this level. So I take it with me. Only things which I take with me, so which I return from the function, will be available in the lower steps of my staircase. So if I do this again, I have to take my bag again, or my package again, back to the next level. So I forgot everything what is here. So the 16 is forgotten. But what I took back is the 32. Each time, if I climb down, I will take the result from the last level up to here. I take it back with me down the hill. And the same again. So if I have this available, I have the 32 available because it's here. It's in my bag. It's in the return value. So, and if I print this now, then you have the 32 available. And this is the really important thing, what you have to keep in mind, that you hand over arguments. You can use these arguments. These arguments are available as long as you're in the function body. If you call the same function again, then you take everything what you hand over with the arguments again for the next step. And each time if you return, you forget everything because the stack will be reduced. So you climb down and everything what you don't take with you. So everything what you let there is forgotten. So everything what you want to use later, you have to take back. And if you're on a higher step here, and if you have a for loop, for example, and you call the function again with the different indexes or things like that, then at each step you do the climb up with different arguments. So the next step will be with the next index, for example, and the next step will be with the next index, but you always just jump from one level to the next. And at each time the new for loop starts. So for example, at this level, if you run the for loop, it starts with 1, then you climb up, it starts with 1, you climb up, it starts with 1, and so on. And at the end criterion, you continue with the loop, and then you climb down, and then you continue with the next index, for example, at this level. And then you climb up again, and each time, at each level, you do the complete for loop. And then you come back each time with the result, if you return it, or without the result. So if you have this image of a staircase or of a stack in your mind, if you do the programming of this recursion, then it will be a helpful thing that you can understand what your program does, and then you just can keep on this level. You don't have to think what happens there. You always do exactly the same. You just think what must be done on one level. So your function reduces. If you would write a for loop, for example, for the whole work, it would be much longer, much bigger, because you have to keep the memory, you have to reduce the memory, things like that. But with the function, it's automatically done. And therefore, you just have to think what is necessary at this level, and then you call yourself, and you do exactly the same on the next level, like we did here with the number 2. And then you do it exactly on the same level. You don't have to think, how do I climb up through the whole thing? It's just you call. But the important thing is that you need an end criterion. Otherwise, you would always climb up. So my end criterion was here, for example, if you reach a number larger or equal 32, and then you climb down. So you need an end criterion. And that's the big principle. So let's continue with some samples, or with a more detailed description of a simple sample. Having this knowledge, we can now start with this task. So the task tells you the following: use the simple recursion demo program from the lesson and change it to understand the principles of recursive calls. So here's the program again. So copy and paste it into your MATLAB script, and then try to understand what happens. Start it with different start values and interpret the output. So don't change it, and just use the different start values, and then change the end criterion, call hierarchy smaller or equal to, and interpret the output. So what you can do is now that you first of all think about what happens if you do different inputs. It's always the best way, because then you can directly think about what are the limits, what are the limitations of this call, so when will it stop the processing, and then you can run it and compare to what you if you get what you expect. The other way is, if you're not so used to deal with these things, you can directly run it and check what happens. So let's play with different start values, and then let's show what happens. So here I prepared this TS recursive, and we can call this clear all and close all first. So we can call this with TS recursive. So I have to call it as a function, and then I can give different inputs. So I focus on positive numbers. Of course, you can also use minus numbers playing with this. So let's start with 0 and let's see what happens. So if you watch this, you will see that the call hierarchy, first output of the call hierarchy is 1. So that's of course true. Here, if we enter 0, it comes into the function. Then it does 0 plus 1. So the call hierarchy is 1. And then it starts the loop with this 1. If it is smaller or equal to, it will call the recursion again. So therefore, the loop will not continue. It will call the function again. So it will call itself again. And then it will call it with 1. So because we have 1 here for the next call. So we start with 0. 0 plus 1 is 1. And then we start here. We call it again with 1. So the next call, the next step on your staircase is with a 1 in your package. And then we have 1 plus 1 is 2, and we start the loop again. So the first loop counter is 1, but 2 is equal to, therefore, we will call again our function. So it starts with 2, 2 plus 1 is 3, and then we start the loop again. So 3 in this case means that it is larger than 2, and therefore we don't call again. So in this case we have 1, 2, 3, and if we have 3, we continue the looping. So we have loop counter 1 is still greater than 2 because we don't change the call hierarchy. Loop counter 2, still call hierarchy 2. Loop counter 3, still call hierarchy 2. And if we finish the for loop, we return to the previous step. So we jump down. We jump one step down. If we jump one step down, we are again at call hierarchy 2 because we forget what we did inside the function, and for the call we used 2. So therefore, at the position 2, we again start the loop. If we have 2 plus 1 is again larger than 2, therefore we run the loop again. And this is done several times. And you can play with this so that you see the differences. So if you want to see just one run, then do, for example, call hierarchy 2, because then you have exactly the situation where one complete for loop is used because the recursion will never be called. So if I directly use 3, for example, it will also run the complete recursion because it just focuses onto this conditional statement, and the loop will always be processed, but the call hierarchy, you see, changes, and as long as it is bigger than 2, it will not start again. So if we go to 1, for example, here to the starting point of 1, then you will see that it climbs up to 2, 3, and then it runs a complete loop. Then 2, 3, it runs a complete loop. 2, 3, and so on. So it does this 2, 3, 3 times, because each time when we call this, we are at each time of this, or at each iteration of this loop, we do a call again. So 3 times you will see the same sequence here, and each time you have a complete run through the for loop. Okay, what you see here is you see the loop, the external loop, which is created by the first call of the function, because each time at each iteration you call recursion again, and at each return, or after each return, you add the next iteration step plus 1 to the loop counter so that it runs again. So this is the first call, 1. This is the second call, 2. And this is the third call. So you have 3 times the for loop in the first call, and you have 3 times the for loop in each second call. You have to play a little bit with this stuff to understand it. I know it's difficult as a beginner, but it helps you tremendously if you have iterative processes, because you don't have to create very large functions or for loops to prepare, for example, backtracking or deep search mechanisms. So the second task what we have is we should change the call hierarchy here, so that we have a different condition here. So for example, if you change it to 1, it will stop earlier. So let's start with this, and you will see that you have no change anymore, because of course each time if you have a number which is larger than 1 or equal to 1, it's exactly that you just call it 1. If you change it to 4, for example, and you start with a 1, then you have 3 times, or each run you have 3 calls, and all 3 calls count this call hierarchy up to a maximum of 4. So therefore you have a large output. So if we keep the 2 here, and if we change this, then each run will stop after 5 repeating iterations. And if we let it run with 1 again, then you will see that each step counts to 5, and that you will have 5 repeating calls. Okay, so play a little bit with this stuff and train yourself so that you understand the principle. What you should always keep in mind maybe is this staircase scenario, because each time if you climb up, you create a new memory block. It's like a new paper sheet on your stack where you can remember things. And each time if you jump down from a higher step, you put this away, you throw this away, and you forget everything what you had on the higher step, but you jump back to this level which you had already. Though therefore you can remember things with this, because the stack remembers these things, and therefore you maybe remember the stack situation in the languages theory. It's the same principle. So you can remember, you can count with it, and with these additional mechanisms of memory, so that you can create matrices on your way, you can remember situations which existed before. And things which you want to remember through the whole process, you have to return with return values. So otherwise it would not be kept. So task number 3 also directly deals with this. So you got this as a Christmas contest, Christmas programming contest, and now we will do the solution. I will use an already existing video which I cut in here now, so that you see how this program can be created with the use of these recursive calls. Let's read first of all the task. So write a program to find all solutions of the house of the Santa Claus using a brute force complete testing with recursive calls. So this deep search mechanism or backtracking mechanism. Return the number of possible solutions. Think about a more effective solution. The more effective solution is already shown in the lesson. If you think about symmetries, so if you think about symmetries, you don't have to test all of the starting points, and therefore you speed up. In our case, you double the speed, because you just have to do 3 starting points. If you watch this graph, you can use a line function which draws this line, 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 and this line. So the line function, if you don't remember, watch the video about this in the theoretical lessons, uses the x1, y1, x2, y2 in a combination where the x points or the x-axis parts are in a vector in the y-axis parts. So line in a vector x1, x2 and y1, y2. So therefore we need the definition here. For example, in this case 2, 2 and 2, 8 is the first line. And then 2, 8 and 5, 11. And then 5, 11, 8, 8 and so on. So what we can do now is we just create a matrix which defines these lines. So each line in the matrix is the x1, y1, x2, y2 of this line. So if we do this, we can simply make the following. We define a house graph, and then we say 2, 2 to 2, 8 is the first line. So 2, 2 to 2, 8 is the first line. And then the next line is 2, 8, 5, 11. 2, 8 is this point, 2 in the x-axis, 8 in the y-axis, 5 in the x-axis, and y in the 11 in the y-axis. Sorry. So, and with this we can create a complete matrix which represents all of our lines. So remember, it's just x1, y1, x2, y2. So if we want to plot this first line now, we have to take this and this as an x1, x2, and this in a vector as a y1, y2. And then we can use the normal line function to draw this line. So before we do this, as in each script, I stored here in Nicolaus step by step, we do a clear all, close all, and CLC. So if we run this, we will have the function available that it creates the house graph. Sorry, it's not a function, it's a script, of course. We have the script available which creates the house graph. And now we can use the line function to create the different lines. So it's quite simple. What we do now is we create a line function where we take for the x, for example here, this element and this element, and for the y's we take this element and this element, and this is our first line. So if we do this, you will see that we create a plot. So, and with the same situation, like here with the same calls, we can draw all of our other lines. So we make hold on, and we draw our other lines. The next one, we just have to change the index into our matrix. So we're now going to the next line, which is the next line in our graph. And then we go into the next line. And the next line. And the next line. And the next line. And so on. So see what I do manually here is predefined for a for loop. Because we just change always the index here, and it's quite nice. It's a counter or an index change through all of these indexes here of the lines of the rows. So we have now this nice plot, and here is our program for this plot. So we can copy this, and we copy it into our program. So if we create a figure here, then we have the program which creates our task program for the first task. As I said, this is a predefined situation for a for loop, so therefore we can change this to a for loop. So let's create this for loop. It's quite simple. We have a for loop. We use a new counter or index iterator. We call it line count, and it goes from 1 to size of this matrix house graph, and I take the first dimension of this. And then I just have to use one line call here, and instead of individual indexes of the lines in the graph, I use this line count here. So with this, I have everything what I need for the drawing. So let's run the program. You see, everything works. So what I can do in addition to that is that I beautify this. So for example, I can change the axis. So if I go back to this and if I watch this, it would be much nicer if it is equidistant and if I have it really with some borders around and things like that. So we can do this in a very simple way in MATLAB. So we already remember the x-lim and y-lim where we define the limits. So if we do this, I can say I want to go from 0 to 10 in the x-axis, and I want to go from 0 to 12 in the y-axis. So if I do this and if I run the program, it will create this image. So now I want to change also that I see all of the ticks here, so all of these single lines, not only steps of 2 here. I can also change the scaling of this axis. So therefore we can add a change of the properties, and if you watch the videos you will see that we already used this once in the theoretical lesson. You can set the property of a special figure if you use the figure identifier, and here this is the current figure identifier, and then you have to set the property always with a pair of an identifier and the value. So in this case I set the y tick. The y tick is here the number of lines which are shown, these intermediate lines which are shown here. And with a x tick, I can do this in the x-axis on the current image. So if I do this, you will see that we will get a new image where we have the individual ticks at each integer number. And then we can create an aspect ratio so that the house looks in the ratio similar. And we can do this if we set the aspect to 1, 1, 1. If you want to know more about these functions, then have a look into the MATLAB help pages, because there everything is explained. So with the aspect 1, 1, 1, you set all dimensions x, y, and z to 1, which means that if you have here, for example, a 2, it will be that one line in the x will be 2 lines in the y. Here we have 1, 1, 1, which means one line in the y-axis is actually the same like one line in the x-axis. So this is our drawing, and this is our solution for the first or of the first task. Before I continue here, I want to replace this line function with a known line function, which helps me to simplify the output so that I have a different bold style or line width and a different color of the line. You can of course use the properties with these property pairs, but I created an own function which is called T.S. Nikolaus plotline, where I have the same input like the axis, and I just define the line color and the bold style. So the color is the color which I plot, or before I plot I do a delete, which is white, and I plot it with a new color, and I do a bold style. So I always set the width of a line, and if it is 0, then I set it to 5. So I always set the width of a line, but if it is greater than 0, I use it for the plotting. So then I have the line width. Okay, so color and bold style gives me a possibility to set it with one call of this function, and therefore I replace this line function with my new function. So it will be then this one. So please compare. This is exactly the same like this. So it's like with a line function, and this is exactly this. So these are my x1, x2, y1, y2 vectors, and I just add the color and if I want it bold or not. So in this case, this is the new functionality. So if I run it, I will get the same output as before, just with another possibility. So for example, if I set it to 1, it will look like this. So therefore I can draw a different width of a line, which is predefined to 5, or I can draw it with a line width of 1. So in the first drawing, in the first output, I want it like this. So what else do I need? If I want to identify which way I want to go in the next step, I have to remember which line I already passed. So therefore I have to create an additional memory for the remembrance, or for the memory if this line is already passed. And therefore I do it in a very simple way. I extend this matrix with an additional column. I add an additional column vector at the end here as an additional new column to this house graph matrix. So this can be done very simple. If I create a new matrix where I combine the existing graph with an empty vector created by zeros. So I create a new vector which has the size of the house graph, the first dimension, which is the number of lines or the number of rows, and with one element in the column range, and I add this to the existing. I use a comma here so that it is in the next column, and I add this so that I get an additional vector where I can make some marks if the line is already passed or if the way is already colored. And then before we start, we have to do an additional thing. We have to find all starting points. So if you think about, you can use symmetries or things like that to simplify, because the house of Nikolaus here in this case is symmetrical, so that you just have to check this, this, and this, because this is exactly just a symmetry of the other edges. But in our case, we want to really do a deep search through all of these elements and therefore search all of these points. What we have to do is we have to run through this graph or through this description of the graph through each line, and all of these are points where we can start, and then we select all of them. So we create a list of all of these points here, and then we delete all elements which are duplicated. So all duplicates are deleted. So therefore I write a for loop which runs through this graph. What we do is, I know that I will end up with a number of start points, because I always have 2 points here, and therefore I will have the number of lines times 2 as start points in the beginning of the calculation. And then I will do a loop where I identify all of the start points. And this is quite simple, because I take the first point and I take the second point in this line. So why did I use this start point counter? Because I have to use 2 different indexes. The first index gives me the line here of the house graph. The second index, which I start with 1 here and which must always be the double of this here, gives me the position where I have to copy the found point to. And after this, I will have a list of all possible points where I have duplicates in. So let's run the program. If you check the start points here, you will see that now we have a list with duplicated points. And if we now can delete all duplicates, then we have all of the possible start points calculated out of our original graph description with the lines. Finding duplicates is also a really simple call of a MATLAB function. So you have not heard before of this because we have not done this, but I always told you, if you have such a situation that you have to do something which you don't know at the moment, don't start writing your own program. Just search if there is already an available function offered by MATLAB. And it is. The function is called unique. And what you just do is you assign the result of unique to the start points. You hand over the original list of the start points, and then you tell if you want to find unique or duplicates in the rows or duplicates in the columns. And if you do this, then, so I just copy here to the existing elements, and I run it onto the existing elements in the workspace. And if I show this, then you find all of the 5 points which we will have at the start point. So watch the graph. These are the start points and the coordinates of the start points. So this is exactly what we want. And with this, we can now walk through all of these start points, and we can call a function which does the recursion. So before we do now the call of this function here, we have to create this function. And I prepared this function, and I will explain it here, not step by step, or I will not create it step by step. I will explain it step by step with an existing program. So what do we have to do? If you watch the graph again, we do at each point we do the same decision. So if you are here, then we have to find all possibilities. So we run through all of our lines here, and we check if the starting point, if the current position is either this or this, because we can walk the line in this direction or in this direction. Then if one of these points, x-y combinations, is the current position, and if it is not yet visited, then I can use it. And then I use the corresponding opposite point as a new current position, and I call myself again. So again, what I do, if I'm here, I check which possibilities I have. For example, in this case, from 2, 2, I can go to 2, 8, or I can go to 8, 2, or to 8, 8. These are these 3 lines. And then I follow this line. I use a new position, so I jump, I change the current position to this endpoint of the line, and then I call myself the function again and do exactly the same. So before I do this, I have of course marked this line as visited. So before I do the call, I have to set the marker in the 5th column of this house graph, which we extended, to 1, so that I know, okay, I have already visited it. Remember, go back to the staircase situation. If you go, or if you call this function, if you go one step up, then we take everything from the lower step to this higher step, and then we can use this. And then we start the same again. So we run again through all of these possibilities, and we check, is there a connection point? So at this step, for example, at the position 2, 8, we now check, are there connection points? So from 2, 8, we can go to 2, 2, so we can go backwards in this direction, but it's not possible anymore because our marker will be 1, because we came from here. We can go from 2, 8 to 5, 11, and we can go from 2, 8 to 8, 8, and from 2, 8 to 8, 2. So these are these 4 lines. So we have always taken into account that we can start from here, or we can start from here and go into this direction. And this we have to always visit, or have to always check, and we have to always check if it is already visited. But the rest is always the same. If we do a new decision, we select the corresponding point of this line, and we mark that it is visited, and we call the function again until we reach the end point, for example here, where all of the lines are already visited, and then we return. At this point, we can check if we reached a situation that all lines are marked. So at the end, if we do a return, or after the return, we can check if all lines are marked. So if the whole graph or the whole marker vector is with 1s, and then we found a solution. So we can remember the solution, we can add a 1 to the counter, and then we can go back. Going back, so returning from the function, after the return from the function, we have the previous situation. The only thing is what we have to change is that we cancel the mark or this visiting marker, so that we delete the last line again, and that we do unpainting. So let's have a look into the function. I prepared a backtracking function which is called his Nicholas backtracking, and what I hand over is the current position and of course the house graph. I also add if I want to plot or not. So all of these things here are just things which are in addition. So for example, if I want to do a plotting, I have here a number which is greater than 0. I can select a pausing time, so that after each plot I have a short, or after each selection I have a short interrupt, a short waiting pause. I can also add the current path. I can add the found paths. So if at the end, if I want to remember all of the paths which I found, I can hand it over, because I have to add always a new path, a new found path to the list of paths, and I can count the number of steps which I did. So what I return is the current path, the found path, and the number of steps. So it's what I want to remember and what I need for the further operation. So in this case, you can ignore these figure selections. If you want to always plot it, then you can ignore this. But I select only a plotting if it is greater than 0. So therefore, I always do at each plotting, I do a check of the figure, for example, here and so on. So you have to do a plotting. I always check if I want to plot. So ignore this if you just want to see the pure graph. And then I do exactly what I explained before. I go through all of the lines in the graph. So I go through all of these lines here, and I check if the current position which I got from here, and at each point of, at each edge, at each node of this graph, I do the same decision. So I have a current position. It depends on the previous steps, but for the calculation, it doesn't matter. So I have a current position, which is an XY position, and I check if the current position is either the starting point of the line or the end point of the line. And if it is a starting point or the end point of a line, then I can do a plotting in red. So I go this way. So I path this way. And I have to remember, so you can also ignore this pausing. It's just used for the plotting. After each plot, I will pause a little bit if I want this. But you just have to check this. So if it is a start point or an end point of the line, and I walk through all of the lines, then I plot it in red, and I mark this position where I'm at the moment, where I am at the moment. So at this current position, I mark as visited. I change the current path so that I have the current path plus the line count, and I change the current position to the or I remember the previous position, which I take from the current position, so that I can jump back. It's used for the unplotting, for example. And then I select the new current position. So I remember the previous, I remember the current position with the previous position, and then I really go this way. So this is just for the plotting, and this is for my own bookkeeping. So I go here, I go this way. So for example, if the current position X and Y corresponds with the house graph 1 and 2. So with this, I will select this as the next current position. So I go this line, and if it corresponds to this, I will use this as the next position. I go in this direction. So the new current position in my case, if I start with 2, 2, and if I walk this way, then the new current position will be this. And this is exactly this selector here. And then I sum up the number of steps, and I call myself again with this new current position, with the same house graph, of course, and with the same things which I selected from before, just with some changes of the current path, the found path, and the number of steps. And if I call myself again, then I start here again with a new position. I go into here, I do the same decision, I run again through all of the elements, all of the lines here. So I have a new state or a new level of my staircase, and I run through all of these elements again, and I do for all of the elements, I do the same again. And this is why it is a deep search or a backtracking. The backtracking comes now if I reach a situation where, for example, I cannot find any more a following position. So if all of the things are marked in this case, so if I cannot find a new position, so if all of the lines are marked, I run through all of this and all of the lines are marked, I will end up here. So I will end up here, and then at the end of the for loop, I will do exactly what I told you. I will remember the found path if all of the lines are marked. So if all of the lines have a mark here that, or if all of the lines have an identifier here that it was visited or that they were visited, then only if this happens, in this case, if the sum of the elements in the last, so I always set 1 if I pass it, if I color it. So if the sum of this colorization memory is the same that then the complete size of the graph in the first dimension, so of the lines, then I will do the following. I will draw the graph completely with green. I will wait a little bit and I will redraw it with red, and I will remember the found path. So the current path, so the steps through the graph, the current sequence of lines will be then added to the found path, and this found path will be returned, and then we'll go through this and we will return the function. So if we return the function, we will come back to here. So we will go one step back, one step down of the staircase, and this one step down in the staircase will continue with the previous citation. Only things which we already return here will be used for the continuous steps, and then we will continue here. So we will do an undrawing. So we will mark the previous line, so the line which we colored here in red, we will color again in blue, because we have to go backwards, and this is this backtracking. And then we will change the marker of visiting, this identifier. If we have colored this line, we will reset it to 0. We will change the current path. So the current path, the end of the current path will be deleted. So the last add on to the current path will be deleted, and then we will go to the previous position. Here we remember the previous position from the current position, and here we go back to the previous position. And then we continue. As long as we do not finish the for loop, we will continue with the next element on this specific level of our staircase. So if you always keep this staircase scenario in your mind, you can really nice identify where we are. And then we go to the second line, and for the second line at this individual level of the staircase, we do the same, and we go to the next step and we run again through all of the possibilities of the lines and so on. And therefore we always climb up, climb up, climb up, and climb down, climb up, climb down, climb up, and so on. Therefore it runs through all of the elements, and this backtracking mechanism calls always itself with new starting point. Starting point is always the current position, and it remembers things which we want to use later on. So try to use this program, try to understand this program, and then run it. Okay, so again, very simple in the steps, but very complex in the understand, because you have to think in this recursion method. So you call yourself and you create always a local memory with a new situation. And this is what you should keep in mind. So let's run this program. I cannot directly call it from here. I have to do it here in my program. So what I do here is I will create empty elements for the things which I hand over and which I return. So if you remember these things which I return and these things which I hand over, I have to prepare here. And then I run through all of the elements which I have in the matrix, all of the points, of course. So this means everything what I created here, so the start points are this iteration points here. So I run through all of the points and I do nothing else than calling of the function. So again, it's like inside, I call this function, I hand over the first starting point which I take from here. It's just an index counter through the start points, through all of the possible points. I hand over the house graph which I created here with this extension of the identifier of if I visited it, so with this marker here. And then the rest is for the plotting and the rest is for the housekeeping. So these are the elements which I also get back. So here I have then a list of all found paths. Here I have the number of steps, and here I have the number of, or here I have the current path to remember. And then I can print this, and I will get the number of, or all possible solutions. So let's run the program. So what you see is now this backtracking, this green lighting and the red. This is this if at the end of our backtracking function, and you see it walks forward. Each time if a red line is painted, it will go step up in our staircase. Each time a red line will be cancelled and will be drawn with a blue line. Then it goes back to this and takes the, or replaces the current position with the previous position. And it walks through all of these possibilities, and at the end you will get 88 possibilities. So 88 possible ways. It will cost a lot of time here because I always have this 0.05 seconds of waiting time. So I will interrupt it here. And if I, for example, don't draw it, and if I have no waiting time, then it will run through the program. It will do all of the checks, and it will find all of the solutions. So if you want to also remember how many possibilities you find, then you have to also do a housekeeping of the number of possibilities. I do it implicitly because I collect the found paths, and then I can just use the size of found path, comma 1, and then I will have the number of possible found paths which I can go or which I can find in our graph. So therefore, I don't do an explicit housekeeping of my number of solutions. So that's it for today. I hope you had fun with the programming. I know that the recursion is a very sophisticated thing. For beginners, it's explicitly difficult, but if you understand the principle behind, so that you have always a local memory, and this local memory is forgotten if you return from the function, then you understand the principal characteristic of a function. And this is what the background of this programming is. And if you understand this algorithms technique and also these deep search mechanisms, which is something like a brute force attack to solutions, then you understand also a lot about algorithms. And you can also use this knowledge for other graphs, for optimization processes. Nevertheless, for optimization processes, you don't use unweighted graphs. So, for example, if you want to find the path through a city on a road map, then you have to use some weights on the streets, like the distance or the difficulty of the street or the type of the street, so that you can improve your decisions. And then you have also other possibilities to optimize search mechanisms through a path. But for a starting point, this program is quite nice, and therefore I hope you had fun, and see you next time in the lesson. So bye bye and enjoy the time.